So we're dealing with vapor compression refrigeration. Try to give you a very practical, hands-on look into what real refrigeration systems look like. It's too broad to really cover all of the applications and areas, but we'll talk about what an evaporator looks like. TXV or the capillary tubes, we'll show you some of those. Talk about, again, that split system. You have an indoor unit, outdoor unit, the condensing unit on the outside, the furnace on the inside. Then we'll talk about mini-split packaged, and if time, we'll solve a problem and talk more about other refrigerants. So this is the typical home, apartment, air conditioning system. So you'll have a split, meaning the coolant lines can run a long distance between something on the outside, something on the inside. On the outside, you have the compressor and the condenser. On the inside, you have the expansion valve. And very close to the expansion valve, we have our metering device. The evaporator. We have an expansion valve very close to it. So it meters the flow of refrigerant, releasing it into the evaporator. And a lot of them have some simple feedback system to them so that it can shut down the flow or restrict the flow or reduce the flow of refrigerant into the evaporator. The evaporator, typically a coil, a lot in the homes. You have a blower motor, the airflow is up and over across the coils. We have two lines. One is called the suction line, one is called the liquid line. Which one is the larger diameter? Suction line is the larger diameter, true? Which one is the liquid line? Small diameter. All right, here's the first clicker question. Answer A or answer B? Suction line or liquid line? Which line is hot to the touch? Which line is hot to the touch? I will start it now. Is the line that's hot called the suction line or the liquid line? Well, last chance to throw your votes in. And let's take a look. And here you go. So we have a bunch of people that say it is the liquid line that is hot. They are correct. Now, that just leaves which line is cool. Which line is cool? The suction line. The suction line is cool. Which line is typically insulated? We'll start the next clicker question. Is the suction line typically insulated? Answer A. Or the liquid line typically insulated? Answer B. Maybe I should say answer C. Both are insulated. All right, we're stopping and we'll see where we're at. Okay, so you insulate the cold line, the suction line, because it's easier for the compressor to compress cold vapor versus hot vapor. It will cost more work to boost the pressure of something that's a hot vapor versus a cooler vapor. And it helps the compressor run cooler as well. But let's go ahead and select A. There you go. Why don't we insulate both lines? Insulation should be good. Well, the stray heat transfer from that hot liquid line is helpful. You don't want to insulate both. Okay. This is that thermostatic expansion valve. Now, a couple things. The inlet to it versus the outlet to it. Can you see a difference in diameter? Okay. It comes in high pressure side. Is this the high pressure side? Or is this the low pressure side? The inlet, high, small diameter liquid coming in. When there's a big pressure drop across the valve, this is the valve right in here, then it flashes. Now you have some two-phase refrigerant. It needs more room. It needs a bigger diameter. Okay? And then the rest of it's going to evaporate. Well, what's this coiled up thing and then a big bulb on the end of the coiled up thing? It's a sensor detecting the temperature where you want it. So you put that bulb somewhere and you sense the temperature. That bulb has refrigerant in it. the line that's coiled up all has very little refrigerant in it, but the bulb has the majority of the refrigerant in it. If the bulb gets hot, the refrigerant expands. If the bulb gets cold, the refrigerant contracts. That's just like a gas, a vapor does, okay? Now, it's connected to a big top disc on the top. It's a diaphragm. So it's a diaphragm. So we sit like here, we have a top to it, you have a little connector, and when the bulb is cold, the pressure is low, and the diaphragm wants to deflect upward. Okay? It wants to deflect upward. When the bulb is hot, it wants to deflect downward. And you connect the diaphragm to a shaft, and maybe you at the bottom of the shaft you have some wedge type, and it sits in a seat. And if this pulls up, it seals off such that the passageway is blocked. And if the diaphragm goes down, then it opens it up and lets more refrigerant go through. That's what's happening. It's a control device, a metering device. It's an expansion valve. Where is this temperature sensor located? Typically, you put it. You can kind of see it. Let me clean this up a little bit. The coil comes off, wraps a little bit, goes way over here. There's the bulb right there, and it's taped. Taped to the liquid line or the suction line? Suction line. If the suction line, the stuff coming out of the suction line is too warm, it says, I need more refrigerant. Send more refrigerant to the evaporator. The bulb on the suction line is too cold. I've got too much refrigerant. It's flooded. Stop sending refrigerant. Meter it down. Toggle it down. Okay? So this is a metering device. It's typically a TXV, acronym for it, thermostatic expansion valve, or TX valve, or TEV. There's different abbreviations, different terminology. So it's a precision device. They don't cost much because they mass manufacture them. And it's designed to regulate the flow of liquid refrigerant into the evaporator. Here's another way of doing it. It's with capillary tubes. There's no TXV. And if you look at the back of your refrigerator in your house, it's typically a capillary tube. Things that run more constant are typically capillary tube. Things that turn on and off and need to modulate for control are typically more TXV. Okay, so here you bring in the liquid refrigerant in the liquid line. It comes in, and this just splits it out. There's no pressure drop right here. It just splits it out into some lines which are called capillary tubes, and because they're so long, they're typically coiled up so they can take less physical space. And then they go and bleed into different parts of the evaporator. So the pressure drops in the long length of a small diameter tube. And engineers have tested and measured these capillary tubes, and they're well characterized for flow of different refrigerants through them. So if you know what your high pressure needs to be, your low pressure needs to be, your flow rate needs to be, this is the length and diameter of that capillary tube, and it's well engineered, well tested. And so boom, there they go. So it's a throttling device. Doesn't look like a TXV, does it? But it's a capillary tube. Here is just more about that throttling device known as a capillary tube. The key is it comes in at high pressure. The high temperature doesn't, we'd like it to come in as a low temperature as possible. If it's coming out of the condenser, it's going to be hot. And the key is it goes to low pressure, and just because of the physics of the fluid, the pressure temperature relationship of the fluid, it wants to go into the vapor state. It wants to then, if you drop the pressure, it wants to vaporize, hence it's going to have a lower saturation temperature. So you can see how they talk about throttling device and obstruction to the flow, tremendous pressure drop, then because of the change in the pressure, the boiling point of the refrigerant drops, and it starts to evaporate. You flash. Some of it goes promptly into the vapor to bring the whole substance, the whole two-phase fluid, to a lot lower temperature. And then you're ready to, with that low temperature, evaporate the rest of the liquid and provide cooling. We're done with metering devices. We talked about the split system. There's just, I want to expose you to a mini split in the AM section. 2 people said they live in homes that have mini splits in them. I think you may see more of them in the future. So what it is they'll have one big condenser compressor unit outside, or maybe even 2. And they'll have multiple line sets running to these mini air handler evaporators that are located in a smaller zone or a room or a bedroom, maybe a master bedroom, or maybe somewhere where you really want to have better climate control. Okay, and so right in here then it can be mounted on the wall. How much duct do you have running in the attic? Not, right? So you don't, and all ducts leak. All ducts leak. Don't think that they don't leak. And if you don't believe me, go up in the attic of your house. You'll find duct leaks up there. They only leak 5% of the airflow through it, but 5% is quite a bit. Okay? Or it may leak 10% or more. Or my brother one time had to go to look at a house that was a rental property in San Antonio. And he had to go up into the attic, and I went with him to help him out. And somebody had long ago cut an inspection hole in ductwork and then taped it up. After about 5 years, the tape gave way, and that person was blasting cold air right into the attic. It's not uncommon to have a good 12-inch or 10-inch square hole in your ductwork just opened up into the attic. So if your home is not doing so well, keeping you comfortable in the middle of August, you might want to take a peek up there in the attic, see what's going on. Anyway, so you'll have multiple of these in different zones. The beauty of this is if I don't have a bedroom in use, turn it off. You can save a lot of money by not driving your gas-guzzling car. You can save a lot of money by not running your air conditioner or turning off zones in your house. That's why this is so helpful or beneficial. As well as let the temperature float up. Let it be warmer in that zone versus the critical zone. Let it be comfortable. You want to sleep at 68? No problem. Turn down your bedroom to 68. Go in there and put a parka on and sleep. Or whatever temperature you like, right? But if your living room, nobody's in it from midnight till 8 a.m., let the temperature float up. You can save a lot of money. So I think these are going to become more popular. Anybody have a home or apartment with a mini split? 1, 2, 3, 4, really? So it's even more popular than I thought.
In Mexico, it's really popular.
Very popular. Is it because of the price of energy in Mexico, the utility they need?
Just for that, so you can zone out your house.
There you go.
If you need more cooling in the specific room.
Let it really blast you and make it comfortable. How many people own a house? They say, well, I got to turn down the whole system. I go in that back bedroom, it's a refrigerator, but I'm sitting in the living room and I'm sweating. Well, you got to shut the vents, but it still doesn't typically balance as well as you'd like. Yeah. So anyway, mini splits. The next one I want to expose you to is packaged unit. All right. In the mini split, as well as the split system, you had the compressor, condenser far away from the evaporator and the expansion valve. Here, put it all in one package. So what you do is you bring the warm air to it and you take away the cold air. And so everything's in this package, all 4 components, typically sitting outside or on the roof somewhere. It's a packaged unit. Now the problem with this is that you have to have typically big ducts cutting holes in the wall of your house to get out to it and then back into it. And it takes a lot of cross-sectional area to move a lot of air, so you have big ducts that penetrate the side of your house. So you can have a package unit. It's very rare to see a package unit in a residential application. Oh, you can, but it's very rare. It's more common to see them up on the roofs of commercial buildings where you have just a lot of square footage, and it's maybe just a warehouse type, or you walk into a retail shopping space. They just have a big roof and not too many floors, or 1 floor only. And so you'll just see looking down a whole line of these packaged rooftop units. They're built up on this little stand, so in case you get a lot of water and other things, it doesn't have a leak there. And then they have a little hood typically to bring in some outdoor air if you want to have some outdoor air. I would call it fresh air, but it's sometimes not all that fresh. It's just outdoor air. It's not clean air. It's just outdoor air, okay. It may have a lower CO2 content because it's well mixed outside. Typically, they have a coil over here. That's going to be your condenser coil. You're going to draw air over and up to reject air, heat to the air. But packaged in here, it's kind of hard to see much, but you're going to have an evaporator. And you're going to take air from below, that's warm, put it up through a device, and push down nice cool air. Sometimes it's just not much duct work to it. You just suck right over here and blow down over here. And sometimes they'll have little ducts running for some length. So if you just take a look at it, it's the air that runs over the condenser and the fans to reject heat. There's nobody puts and sprays water to promote the cooling. Our water's so hot or so hard that you would have such a big deposit up there, it would be a disaster. Nobody does that. Not in Texas. Not where we have hard water. It would be all white, crusted in just a few weeks. But this is the illustration I had. And so here is your compressor, and it's going to run to the condenser. Then the liquid refrigerant is going to come over. It's going to go through your evaporator coil, your cooling coil, and you're going to have an expansion valve close to the cooling coil. So maybe you grab some air out of the inside of the building, bring it up. Maybe you have some outdoor air you mix with it. Maybe you regulate, mix it. Or there's another thing called economizer mode. Some days it's just pleasant outside. It's dry and it's cool. Shut down the compressor, run the fans, just bring in that nice cool air. Throw this air out some way with dampers and just throw it in. That's economizer mode. You can save a lot of money. And every one of these systems have economizer mode. But only a few days or a few hours in the days can you run it like that. But the engineers are smart. They can save some money that way. But otherwise, you bring it up, you condition it, and you throw it back into the building. That's it. And so you just get a crane, and you can just pick that up and put it off and replace it, upgrade, and do all sorts of things. So that's a packaged rooftop unit. Let's solve some problems now, huh? So we have refrigerant 134A. It's a working fluid in a vapor compression refrigeration cycle. It has 2 evaporators. So this is evaporator number 1. This is evaporator number 2. The saturated liquid exits the condenser. So this is our typical sat liquid at 36 degrees C coming out. The refrigerant in the evaporators are -4 degrees C, and -26 degrees C. First clicker question. Is the -4 degrees C, is that for evaporator number 1 or evaporator number 2? Answer A or answer B? All right, I just started the clicker response. So the question is they say, this is at -4, and one of the evaporators is at -26, right? By looking at the illustration, can you tell where is the -4 degrees C evaporator? Is that at A, evaporator number 1, or B, evaporator number 2? Are we all in? Yep. All right, we'll go ahead and stop it then. And we'll take a look. Okay. Congratulations to the 80%. Let's take a look at this. Which is lower temperature? Which one's colder, -4 or -26? -26. Thinking about pressure temperature relationships for refrigerant. The evaporator that has running at the lowest temperature, is that going to be at the lowest pressure? That's the link you got to make in your mind right there. If I go lower temperature, my pressure of the refrigerant in that evaporator has to be lower. Think back to our PT surface or diagram, right? So as I have pressure, temperature, this is how if I drop the saturation pressure, the temperature is going to come down too. Make sense? So lower evaporator pressures mean lower temperatures. Now I see I have an expansion valve, and I have an expansion valve, and I have an expansion valve. That's where I have pressure drops. So which one has the lowest pressure? Evaporator 1 or 2? 2. That's right, exactly. So very good. So this one is at the -4. This evaporator is at -4 degrees C, and this one's at -26 degrees C. For that refrigerant, I can go and look, and I can say that this one's at 252.6 kilopascal, and this one's at 101.6 kilopascal. So I know the pressures. I know the pressures there. Notice also that the temperature of 36 degrees C, I can determine the pressure in the condenser because it's coming out saturated liquid at 36. I look up what's Psat for a temperature of 36, and it's 911.5 kilopascal. So I know 3 pressures right away. Now, saturated vapor exits each evaporator. So this right here, 7, is saturated vapor. Is that our typical assumption coming out of the evaporator, saturated vapor? That makes sense? Yeah, that's a good evaporator. We like it coming out saturated vapor. Okay. The first evaporator has a refrigerating capacity of 1.3 tons. So this Q dot is equal to 1.3 tons of refrigerant. Depending on how you want to show it, it's like from the outside into the refrigerant flowing in through the first evaporator. That's the rate of heat transfer into the refrigerant. Okay? And this is the rate of heat transfer into the refrigerant for the second evaporator, Q dot 1 and Q dot 2. That's 0.9 tons, 9.9 tons. Determine the mass flow rate of the refrigerant through each evaporator. So what is m dot 1? The mass flow rate that goes through the first evaporator. How do I determine that? Suggestions? I like the word balance. Energy balance for a control volume around the first evaporator. And then you're going to find that m dot flowing through that first evaporator is the rate of heat transfer into the first evaporator divided by a change in enthalpy. It's going to come out higher enthalpy than it went in. Did it go in H4? Did it go out H7? Thumbs up if you like it. Good. Now, they gave me m dot or Q dot 1, didn't they? Yeah. I just need the H's. I just have to go and get those H's. Okay, before I struggle getting the H's, m dot 2 is equal to Q dot 2 divided by a difference in H. H6 minus H5. True? H6 minus H5. True or false? Okay, it's true. All right. Now, let's look at part B. What's part B say? The net power input to the cycle. Well, it's only coming in to drive the compressor, isn't it? So W dot C to drive the compressor. Is that going to be the mass flow rate through the compressor times H2 minus H1? Is the mass flow rate going through the compressor equal to the mass flow rate through the first evaporator plus the mass flow rate through the second evaporator? Is that true? From a mass balance. Okay. So it looks like I can answer these questions if I knew the H's. If I knew the H's, that's all you have to do. Get the H's, enthalpy. So make a table. So all your states, 1, 2, 3, 4, 5, 6, 7, 8. And you might as well put pressure, temperature, quality, enthalpy, entropy. We won't do much with the entropy, a little bit, but not much. It's primarily pressure, temperature, enthalpy that I work with. So I know that state 1 is there and state 2 is there, but skip it, get right to 3. I can fill in the table for 3. It's going to take me some time before I get H1 filled out and H2 filled out, okay? Even though the numbering system thinks that 1 should be first, but you can get 3 first, okay? So what information about 3 do we know? Exactly. It's 36 and it's saturated liquid, quality of 0. So I can get this pressure, we just got that one, 911.5, and I can get this H of, let me just write it as H of F, saturated liquid at that pressure. All right, now that I got state 3 figured out, how about 4? Enthalpy is the same. H4 is equal to H3. Just bring that down. What else do I know? The pressure is 252.6. I'll be able to calculate a quality. How would I get that quality at state 4? H of 4 minus H of F divided by H of G minus H of F. And each one of these G's and F's and that are at the pressure of 252.6 kilopascal, or the saturation temperature of negative 4 degrees C. Either way of describing it, because this temperature is negative 4 degrees C. Okay. How about state 5? State 5, can you see how to get state 5? The pressure, which is 101.6, and the enthalpy. Is enthalpy at 5 equal to the enthalpy at 4 equal to enthalpy at 3? Enthalpy at 5 equal to the enthalpy at 4 equal to the enthalpy at 3? The quality will be different. The quality at 5 will not be the same as the quality at 4. True? The pressure is different. That's exactly right. The pressure is different. But is this true that H5 is equal to H4 is equal to H3? Yes. Yep, that's exactly right. Now, we're given 6 and 7 because it's saturated vapor, true? So 7 is the 252.6, quality of 100%. It's H of G. 7 is, no, I'm sorry, I got that backwards, is the 252.6. This is 101.6. But quality of 1, H of G at that higher pressure. Okay, so what are the stubborn ones that are making me work a lot? 8, 1, and 2. Okay, let's do 8. Constant enthalpy, isenthalpic. True, that's right. So, is H8 equal to H7? Yes. What about the pressure at 8? It's the lowest pressure. It's the same pressure as 6. It's the same pressure as 1. It's the same pressure as 5. Is it the same pressure? That's kind of remarkable. Pressure at 5, is that equal to the pressure at 6? Is that equal to the pressure at 8? Equal to the pressure at 1? Yes. Yeah, they're all the same pressure, low pressure. Okay, so we know the enthalpy and the pressure, 101.6. Now, doing it by hand, a little bit of a challenge if you want to get that temperature. And maybe on a diagram, you'll conclude that that is superheated, not two-phase. So when you take a saturated vapor into an expansion valve and drop the pressure, it kind of floats out into superheated vapor. I'll show that on a property diagram. You may be a little skeptical, what's going on there? But it's true, okay? Now, once I've got 8 figured out, now I can go and maybe get 1. What about 1?
Same pressure.
Same low pressure, so it's 101.6. How am I going to fix state 1? I need another independent intensive property. All right, I'll give you I'll get answer A, do a mass balance. Answer B, do an energy balance. Do answer C, entropy balance. Okay, does that make sense? I'll repeat that for you. So, I say I need to get state 1 fixed. You say, Professor, do answer A, mass balance. That'll help it. Or B, energy balance, or C, entropy balance to fix state 1. Mass, energy, or entropy? Are you in? You're in. All right, let's go ahead and get everybody's in. And And do you think there's going to be consensus?
50%.
All right. Well, okay. What's happening here is I maybe should have put a little box there with the letters MIX. What? I have 2 ins, 1 out. When those 2 inlet pipes come together with 1 outlet pipe going out, what's happening? Mixing. It's mixing, okay? It's just mixing. Sometimes they're not going to put some sophisticated little box there. It's just, look at 2 ins, 1 out. They're going mixed. All right? So if I do a mass balance for this mixing, it's the mass flow rate coming from 8 plus the mass flow rate coming from 6 is equal to the mass flow rate going out to 1. I already used that. I already did that. It's not too revealing, so it's really not going to help me fix state 1. I did that. Didn't I do that right here? Right? Okay. What's the energy balance look like if I apply it to this mixing box that's taking 8 in and 6 in and going out with 1? Would it be I'm running out of room here, but let me erase right in here and try and write it in here. Is it going to be the mass balance from 8 times the enthalpy at 8 plus the mass balance from 6 enthalpy at 6 equal to the mass balance 1 enthalpy at 1? Yeah. Yeah. Okay. And this was the mass from evaporator 1. This is the mass flow rate evaporator 2. And we just expand out the mass flow rate evaporator 1 plus mass flow rate evaporator 2 times the enthalpy at 1. True? True? Okay. So let me go back here. At this point in our problem-solving strategy, do I know H7 and H4? I don't know H1 and I don't know H3. I mean 2. But do I know H7 and H4? I already got M.1. All right. Do I know H6 and H5? I got M.2. So it's like done, 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 done. H8 and H6 done. That's how I get H1. So the best answer for this was B. All right. Now, what about state 2? What about state 2? Isentropic. So it's S2 is equal to S1. You get S, then come down. So you know then the pressure 911.5. And there you go. Can I flip to the next page and it'll have the results on there for you? Yes. Because what we want to do is we want to plot these states on a pressure, enthalpy, and a temperature entropy diagram. So here is all the states, the pressures, and the states. Okay? That's the solution. Okay? With the W dots and the M dots and the M dots. Okay. Let me do this. I want to plot these on a temperature, entropy, and a pressure enthalpy diagram. How do I start? Put some pressure lines on the diagram. Because how many distinct pressures are there for this problem? 3 distinct pressures. You have the high pressure, you have the intermediate pressure, and the low pressure. And there's really only 3 pressures. So put on a low pressure. That's a 101 point, whatever it is, 6 kPa. Put on an intermediate pressure. What pressure is that? 252.6. And then a high pressure, and that high pressure is 911.5. What do they look like on a pressure enthalpy diagram? That's right. 101.6, 252.6, 911.5. Can you tell me what's the temperature at which this is changing phase for the 911.5? On a temperature entropy diagram, what's that temperature right there? 36. What's that temperature right there for the 252.6? Minus 4. And what's this temperature? Minus 26. Very good. See that? All right. Now, what states might be easiest to fix on this one? Let's start with 3. That was easiest to calculate, right? 3 was high pressure saturated liquid. Can you see where it goes? State 3 on the diagram. Does it go right here? Then it went to 4 and then to 5. Is that going to kick over with a dash to 4? Kick over with a dash to 5? Where's state 6? Saturated vapor coming out at that low pressure. Right here? All right. Where's state 7? Saturated vapor at the intermediate pressure. 7. Now this one's a hard one, but the pH will help us see it. When you go through from 7 to 8, sometimes you don't know, does it go like this? Or does it go like this? Where's state 8? The 8 has to go to the low pressure line, right? So here's a clicker question. I'll turn it on. Is 8 closer to A or is it closer to B? State 8. State 8. Where is state 8? Is it closer to point A or is it closer to point B as I've shown it? I'm not answering that question until you answer mine. What do we have? 8 is after the expansion valve. What's coming into the expansion valve? State 7. State 7 is saturated vapor. Professor, would it be wrong if I looked at this information right here on this line and used that to guide my choice? No, it would not be wrong. Go ahead. You can use that information available to guide your choice. No more hints. All right, now we're ready to call the question. We have to leave a little early today because of solids exam. So we stop at 45. Is that early enough to stop? Instead of 50? All right, everybody in. Thank you for participating. Let's see where we reside. 100% correct. I know it. All right. Let me ask you this question. Negative 9 degrees C. Negative 9 degrees C. Where would that fall? Would that fall below 26 or negative 26? Would it fall between negative 4 and negative 26? Negative 9. I'm looking at negative 9 degrees C. Would it fall between 36 and negative 4, or would negative 9 be above 36? That was the hint. That was the hint, wasn't it? Yeah, that was it. Oh, that's a trick question, Professor. All right. Sorry if I make it look too easy. So it comes in at negative 9.2 degrees C. So state 8 is right there. Answer B was the correct answer. And we get rid of this. Now, done with 8. Now, what about coming into, I mix it with 1. I mix it with 1. It still has to be on this 101.6 line, doesn't it? The low pressure. So where is state 1? Look at the temperature. So it's going to be right there is state 1. True? It's mixing 8 and 6 to make 1. It's going to be between them. Okay, now I push it through the compressor. S equals S. And we are now at this spanking hot temperature, which is around 55 degrees. Way up here at 55 degrees. Does that all make sense? Get all your states. This really helps you if you get all your states on a TS. Okay, now the pH. All right. Well, where's state 3 on a pH? Did I go too fast for you? Saturated liquid or saturated vapor? High pressure, left side. High pressure, left side. Where is state 4 after state 3? Straight down. Draw a dashed line, irreversible. Dashed line, irreversible. There's 4 and there's 5. Where's state 6? All the way across. Right here is 6. Where's state 7? It's all the way across at the intermediate pressure. All right. Where is state 8? This is where you can clearly see that 8, if I come straight down, that's where 8 is. Right? It's clearer on a pH diagram where state 8 is. Isenthalpic process it's in this superheated vapor region. All right. I mix 6 and 8 to get 1. There's 1. I push it through the compressor to get 2. Look good? Very good. I would put this on a real temperature entropy diagram to show it to scale, and on a real pH diagram to show it to scale. But I'm out of time. Best of luck on your next exam.